Hallo? Hallo, hallo?
Ja, man hört dich. Aber sonst ist nur die Telefonnummer hier nehmen.
Hallo, hallo?
Das wird schon.
Ja. Geht's jetzt? Can you hear me? Hi?
Ich glaube ja,
Du hast den Ton aus.
Ja, ich habe den. Damit nicht. So.
Hello? Great. Could we please be seated and get started? So the first speaker of this session is Maxim Pospelov, and you may be somewhat surprised by the topic. It's not string theory directly. However, there is a parallel conference on dark matter, and we will have this exchange talk from that conference, and Kumron Wafa, who's somewhere here, will give a strings exchange talk to them on Wednesday. So it's a great pleasure to have Maxim here to talk about dark matter identification efforts. Take it away.
Oh, hello. Good afternoon, everyone. It's a pleasure to be at your meeting and represent the workshop or conference called Identification of Dark Matter. So that is a topic heavily influenced by experimental physicists looking for dark matter with underground detectors. And so today I'm going to convey some of the sort of theoretical and thinking about the current sort of dark matter identification efforts, and we'll discuss some of the experimental results released in the recent weeks, and should say that there's so far negative, but very constraining for the models of new physics. And with that, I will set to let's see. Okay, so dark matter is you can identify it at the place where I used to work in Victoria, BC. There is a local brewery that produces beer called Dark Matter, but I was quite taken by the sort of very profound questions that this brewery suggests to you. What's in it? And get in touch. That's the story of direct detection, and who made it, and so on. So this is very relevant set of questions when you think about dark matter, given the fact that we know that it constitutes about a quarter of the total energy density in the universe. And so get in touch with dark matter is a story of direct detection of dark matter. So when we think about dark matter, we know that there is sort of almost ironclad evidence for it in the anisotropies of the cosmic microwave background and in the way how the matter clusters after the recombination. But the smallest energy distance scale at which we observe the dark matter is the scale of galaxies and satellite galaxies, and to make a big step towards attempts to discover it in the laboratory, we need to extrapolate by 19 orders of magnitude. So depending on your model, you may or may not have a dark matter in this volume. So if the dark matter is in some sort of particles that are relatively smoothly distributed, then yes, there will be in this volume. If it's in the form of primordial clumps or let's say primordial black holes, then tough luck. So therefore, we need to sort of get some ideas about possible genesis mechanisms for dark matter, and what we know that it's been in place since the matter radiation equality at the very least, because that's when the first sort of potential wells of cold dark matter started forming. So this is a very busy slide representing sort of main lines of thoughts that people pursue in talking about the dark matter. So at the very early times and conversely large temperatures, when they were larger than the dark matter mass, we can think of the several categories of dark matter. If the size of the dark matter population was normal, meaning that the same order of magnitude as the rest of the species, for example, photons, then this is the weakly interacting massive particles category, but let's say they were present in large numbers, but then depleted themselves through the annihilation into the standard model states. And if this annihilation rate is on the order 1 picobarn times the speed of light, then this comes out to be comparable to observable amounts. So these are weakly interacting massive particles, and the beauty of this scenario is that it's quite forgetful. Aside of maybe some conserved numbers, the initial state of the universe doesn't matter, because there is sort of a universal equilibrium attractor of how many WIMPs you will get, and then the process of their depletion is also quite universal. Then there could be things very sensitive to initial condition. For example, there could be very, very small, tiny fractions of dark matter after the reheating, and then this thermal leakage, so to say, sub-Hubble rates due to the very small couplings populated the dark matter particles to just the right level. So this is the picture of super weakly interacting massive particles, and one could think of gravitinos, sterile neutrinos, and other possibly decoupled sectors or semi-decoupled sectors. These are, let's call it super WIMPs, where super stands for the super weakly interacting particles. Then the abundance could be huge. That's another possibility. And if, relative to photons, if these initial numbers are that big, these particles are necessarily bosons, and they are in the very, again, their interactions with the standard model is very small. They're in condensate-like super-cooled state, and as the universe expands, eventually this coherent field, it's a more let's say, economical description of that starts oscillating, and you get, say, axion dark matter, but there are other examples in this category. So these are all very reasonable options, and there are also, of course, macroscopic dark matter, such as primordial black holes and so on. So, as I said already, the WIMP model is perhaps the most hopeful in terms of discovering a concrete signal in experiment. And one reason is that if you have the annihilation rate of that magnitude, which roughly commensurate with the weak scale, you get approximately the correct abundance. There is no lack of models that will provide such a mechanism of, say, connection between the dark matter states and the stellar model states. The original model of Lee and Weinberg was some form of the neutrinos, massive neutrinos interacting via Z bosons. There is a possibility of, very economical possibility of the Higgs mediation between, say, a pair of scalars and the stellar model. And there are also options that are more complicated and involve additional mediators, such as dark photon particles, that allow actually also to lower the scale of the dark matter states to below a GeV. And one of the most prominent models is, of course, a framework based on supersymmetry, where the lightest supersymmetric particle is stable and the mediation occurs due to the exchange of the superpartners. So this, but one could also have a Higgs mediation, for example. And all these diagrams in the T channel correspond to WIMP nucleus scattering, and this is not a new idea. This was suggested in 1980s. In 1980s, there was a nice paper by Drucker and Stodolsky suggesting that one could use detectors with low thresholds to look for the coherent neutrino scattering, when the neutrino partakes some of its momentum to the nucleus, and nucleus receives a small but measurable amount of recoil. It was soon generalized by Goodman and Witten, or soon realized that this mechanism could be also applied to a search of the stable particles. Like I said, these diagrams in the T channel here. And after that, there was an explosion of activity in trying to detect the dark matter. And while the dark matter has not been detected, these efforts have led to actually decisive measurement of the coherent neutrino scattering on nuclei using the dark matter technology. This is the slide from coherent collaboration from 5 years ago, when they first saw the coherent neutrino scattering on the dark matter style detectors, sodium iodine, detecting 10 kVs of recoil. So with lower threshold detectors, there may soon be detection of neutrinos coming from the reactors that have even lower energy than the spallation neutrino source is here. Very well. So, and then, of course, the development of this coherent neutrino scattering now feedbacks on further on the development of the dark matter detectors. Now, very recently, or let's say in the last 10 years, we saw a very successful program of direct dark matter detection based on scalable dual phase TPCs based on xenon element. Xenon is a heavy element, inert gas, and this is being sort of this technology developed in 3 places in Europe, North America, and China. And there's been a competition of all these 3 experiments, always achieving better and better results. And so very recently, the LZ collaboration has published their data that I will going to discuss shortly. So this has been a very successful program that allows to constrain many models of dark matter in the absence of positive signal. But it also allows to constrain not only the nuclear scattering of dark matter, but also ionization signature with the scattering on electrons. So this is the sort of the scaling up technology is really being pictured here before. So there's a competing group of individuals jumping in size in this cartoon until you reach the final sort of stage where you cannot grow any further. So this is very, very reminiscent of that. We had a sequence of scaling up, and so far it's been very successful. So these are the latest results. So on the WIMP nucleus cross-section as a function of dark matter mass, the best sensitivity you achieve in around 30 GeV, where the mass is somewhat smaller than the xenon nucleus mass, but higher masses are punished by the nuclear form factors. If we sort of try to interpret this this model in terms of the simplest model of dark matter, where I just introduce a scalar that talks to a Higgs boson via a marginal operator like that, we can see that this is actually quite constrained by this set of data. In particular, if you calculate the annihilation rate in the limit when the scalar is heavier than the electroweak scale, this very, very simple exercise. And so is the calculation of the Higgs exchange cross-section. So it's a Higgs force, if you like, between the dark matter and the protons. And the fact that I have if the protons were elementary particles, there would have been a mass of the proton to the 4 relative to the mass of the Higgs to the 4. But because protons are composite, there is sort of a matrix element, QCD matrix element that is somewhat smaller than MP here. So putting it together with the experimental constraints sets the limit on the mass of the dark matter particle to above a TeV, pushing this coupling constant to already sizable values and making it larger, for example, than the Higgs-induced self-interaction coupling. And subsequent experimental improvements may completely sort of push this model out of existence. Then this is for the most minimal model of dark matter. This is a model not motivated by any profound top-down approach, but just by the simplicity and its predictivity. Very soon, well, I don't know how soon, but eventually this process will start being sensitive to models where the particles carry some electroweak charge, but don't have a three-level Z exchange, but instead exchanges via the W boxes or the Higgs exchange induced by the W exchange as well here. So in this case, the cross sections are predicted to be 10⁻47, and in some cases 10⁻49 centimeters squared. This is way down compared to 10⁻49 compared to this plot somewhere here. But there are still sort of daring proposals of eventually breaching this 10⁻48 centimeters squared level, where the coherent scattering of boron-8 solar neutrinos will eventually become a background. Now, 2 years ago, the conference that I'm attending was also here, and it was virtually, and much of it was dedicated, or much of the excitement at that time was dedicated to the xenon 1-ton electron excess. So xenon 1-ton has published a paper that calls it an excess in the low energy data. It doesn't look very dramatic, but there is no look elsewhere effect, because they were were looking for the emission of the exotics from the sun. And with this signature, there was a lot of theoretical activity to understand whether this can be indeed a positive signal from some exotic, not necessarily full dark matter, but maybe subcomponent of dark matter. And what is xenon 1-ton excess? So it could still be a background. It's maybe a sign of thermal emission from the sun, like axions, but here the answer is no, because this is resolutely excluded by energy loss constraints in the sun. Is this a sign of non-trivial interaction of light standard model neutrinos with electrons? The answer is again no, but because that's more or less excluded by the supernovae constraints on neutrino properties. Is it a sign of some new KV scale energy, something along the lines of this super weak particles being absorbed by electronic shells? Maybe, but then the scale of KVs comes completely ad hoc. And then maybe it's a signature of fast particles, the dark radiation or boosted dark matter. So there's all these options being investigated. And in particular, the models where the dark matter is represented by a hidden photon or dark photon, where that has a tiny mixing angle on the level of 10⁻16 or 10⁻15 with the normal particles, seem to fit this excess well. So it's a particle that constitutes a dark matter and couples to the electron with 10⁻15 times weaker than the normal photon, and that fits the excess. That is a little bit ad hoc, and we'll see that if there is sort of there is a strong implication for this excess from the observed observations of LZ collaboration. If this xenon 1-ton prediction for the background is flat, and they identify this peak as something perhaps coming from new physics. The LZ collaboration claims that this peak comes from the contamination from the surface, so the xenon was brought down through sort of transported on the surface, right? And then cosmogenically generated argon-37 gives this peak. That's the statement of the collaboration. We will see if that's the truth, because this peak is going to decay with the 35 days half-life. So we'll see. So if both things are correct, then this peak will diminish, but not completely disappear. We'll see. So that's a bit of an intrigue here. Okay, so in the remaining few minutes, I will talk about the detection of light dark matter. So you can see that if the dark particles are very light, the nuclear scattering is very inefficient. People have tried to detect the scattering on the electrons, and there is a whole new program of trying to develop new materials that will be sensitive to very minute energy releases. So if one MeV particle would have only 1 electron volt kinetic energy, and that's a challenge to detect such energies. So what our group has worked out is actually an interesting possibility that on top of the sort of a Maxwell-Boltzmann distribution of the dark matter with the typical velocity of 10⁻3, there is also a very fast tail of dark matter velocitized by the collisions with energetic particles. It turns out that if the cross-section is at the level of 10⁻36 centimeters squared, or 10⁻37, the opacity of the sun to such dark matter particles is on the order 1, and if a MeV scale particle collides with a solar electron inside the solar core, it can partake up up to velocity of 0.1 from the speed of light that will bring it above the detection threshold. So this way, the sun will produce a stream of fast dark matter particles the very same way as the Stuniaev-Zeldovich effect produces more energetic photons when they're kicked by the hot electrons inside clusters. Using this, we were able to set limits on the unexplored part of the parameter space using this reflected solar flux of dark matter. So I'm coming to the end of my talk, and I wanted to make a sort of, instead of conclusions, a long outlook. What to expect and wait for, and this is entirely my personal perspective. So for WIMPs, we should wait for new results from LZ, Xenon Anton, and there's a next generation of Panda experiment in China, because this being the most successful experiments, like I said. Then studies of electron recoil with LZ will probably settle the issue of the Xenon 1-ton excess. That is very interesting. Then development of low threshold detectors. Currently, it hit a snag because there is some population of unidentified strong excesses at low energy, probably coming from mechanical stress and so on. But that's not clear. And whether this development will continue successfully, this is one of the intrigues in this topic. Now there are also particle physics projects that can bring light to the very light dark matter, such as missing energy signals in Na64, LDMX, and short baseline neutrino detectors. Maybe will be new results from the high luminosity LHC on dark matter. In the super WIMPs, we will see the more clarity with respect to the sterile neutrino dark matter, and maybe some of this fraction and maybe hot or warm dark matter. That this is yet to be understood whether this is consistent with galactic dynamics. What I like about the super WIMPs is that any decoupled sector with a mass gap populated by gravity can have a dark matter, and this dark matter will be inherently unstable. Say if it's a dark glue ball talking to the Stern model via the graviton, so they can decay to say pairs of Higgses, and that decay will result in the fluxes of neutrinos and the gammas. And one thing to watch is association with galactic center of high energy neutrinos and gammas, if that would emerge. So this is an interesting topic. Now there is an exciting topic of ultralight bosonic dark matter, and then we will have basically we have a large number of upcoming axion type experiments that many of them are established, but some of them are brand new, and they're intrigued to see if they can push the limits and cover the axion expectation band. And then will theoretical studies converge to an answer whether unstable string networks, I had to push the word string, considerably contribute or not in case of the QCD axion? This is important because if they don't contribute, then one can make a very, very definitive prediction for the mass of the axion and its coupling. And then there are, of course, other interesting topics that I have no time to cover that refer to the ultralight dark matter with masses as low as 10 to minus 20 electron volts. And then, of course, there are plenty of wonders with the primordial black holes, whether they can constitute much of the dark matter. One of the developments lately was the removal of some of the constraints because they were worked out incorrectly in violation of some sort of, let's say, uncertainty relation. And then that's the end of my talk, and thank you very much. My main conclusion is that diversity of dark matter models create a diversity of experimental signatures, and now is the right time to explore them, as much investment is made into direct detection of dark matter.
Thanks very much for this really nice overview. Are there questions? No immediate questions from the audience. Can I ask one? So you said perhaps the LHC run will provide some further constraints. Can you say a bit more what exactly you expect there to happen?
Well, the LHC has been super constraining as far as the particles charged under the strong group, because you can produce them with large cross sections. As far as the exotic particles in the electroweak sector, that are very, very likely to be connected to dark matter somewhat more intimately, let's say, within SUSY models. There, the production cross sections are much lower, and therefore the sort of this program will benefit from a longer run rather than higher energy. We'll see. Some of the models that I've been flashing very quickly include sort of semi-long-lived electroweakinos, where the charged relics are split from the neutrals by not a large amount, which may result in tracks that disappear or tracks that end in some additional vertex. So this is still very much ongoing. So that's not the end of the story.
Juan.
If we think that the dark matter is a WIMP and will interact only through loop effects, I understand you need to go to this neutrino almost. How long would that take? So
currently, this plot, let's say, if you, I haven't included in my slide, but this boron 8 neutrinos are somewhere here. So with the next factor of 10 improvement, there will be a non-zero number of events associated with boron 8 neutrinos. It will be, however, very difficult to make a new precision study of that compared to the SNO experiment, because that would require building up statistics to a significant level. But nowadays, this is referred to as a neutrino fog, in the sense that not a floor, that you can live with as background because you know its shape and you can describe it well. So there are some ideas of how to scale it up, even being in the presence of this background that you can predict well.
Okay, I think we're sweeping. So thanks very much again, Maxim.